Session will be on deterministic list decoding of Reed-Solomon codes, and Soham is going to list the time.
Hi everyone. So this is a joint work with Prahlad Harsha and Mrinal Kumar. So let's quickly go through what's Reed-Solomon codes are. So you have a fixed finite field FQ, and you have distinct points, n many distinct points, alpha 1 to alpha n. And your message space is all univariate polynomials over FQ of degree less than k. And each of these polynomial fx, you encode basically, you evaluate the polynomial in all these distinct points, alpha 1 to alpha n. And your Reed-Solomon code RS of n comma k is basically all these encodings of univariate polynomials of degree less than k. So naturally the rate becomes k by n, and distance is n minus k plus 1. So now let's talk about what's the decoding history of the Reed-Solomon codes. So because the distance is n minus k plus 1, unique decoding, you have this unique decoding regime where you can, if your number of errors is, or I will talk about agreements. Agreements is at least n minus k plus 1 over 2. Then there will be an unique closest code word. And if you're, and then comes Johnson bound. Here you talk about least decoding regime. So there, if your agreement is at least square root of n into k minus 1, then there will be polynomially many closest code words. So now, what are the algorithms for these two regimes? So for algorithms, the runtime we will consider is polynomial of n and log q. Q is the field size. So for the unique decoding regime, you have algorithm Burley-Camp-Welch, which is a very old algorithm, and it gives you deterministic algorithm in polynomial of n and log q runtime. For least decoding regime, over time, Sudan gave a square root of 2 into n into k minus 1 agreement, but the algorithm is randomized. Randomized, but it takes polynomial of n into log q runtime. And later they improved, Guruswamy and Sudan, they improved the agreement, and it is now square root of n into k minus 1, which is the Johnson bound. But again, this is the randomized algorithm. The main problem is if we just take the deterministic variant of these two algorithms, the running time becomes polynomial of n into n and q, which is a polynomial dependence on the field characteristic. So if the original field where you took the distinct points had super polynomial field characteristic, then your runtime becomes very high. So the question is, can you have better algorithms? So first, let's see how those two algorithms work. Both the algorithms shares kind of similar type of approach. So you have so suppose W is the received word, where alpha is at the distinct points where you evaluated the polynomials, and beta is at the received. Some of the beta is are noisy, it got corrupted, some of them are not. So the first step is basically interpolation, where you construct a bivariate polynomial Q, but you have some constraints. The first constraint is this 1 comma k minus 1 degree. This basically means that your q is a polynomial of x comma y. So you give one weightage to the degrees of x and k minus 1 weightage for degree of y. So basically a comma b degree of monomial x to the power I y to the power j is ai plus bj. So if you want to talk about a comma b degree of a polynomial, just take the max over all monomials. So this is one constraint. And the next constraint is q vanishes at all the points, all these alpha I comma beta is with some multiplicity. And you set these parameters that the 1 comma k minus 1 degree to be at most d and this m, these two parameters you set in a such a way such that for every polynomial which was in the list, which is the close enough to the received word, q of x comma fx should be identically 0. That is y minus fx should be a factor of q. And the next step basically becomes that just factorize q, collect all the factors of the form y minus fx, and from those fx check if it has degree less than k, and the agreement is at least square root of n into k minus 1. So this is the framework. But the main problem is the factorization step. Because all the known factorization algorithms, they run in polynomial of n comma log q runtime, but those are all randomized. And the deterministic variance runs with polynomial dependence on the field characteristic. Even the univariate factorization, those algorithms also have polynomial dependence on the field characteristic. So just running the uh, bivariate factorization completely, just blindly, will not give you proper deterministic polynomial of n in n and log q runtime. So this is a still open problem that any with like by factorization algorithms with any arbitrary fields without any assumptions. Like even for quadratic polynomials, univariate polynomials, we don't know any algorithms. So what we gave is basically the second step, the factorization algorithm. We gave a deterministic algorithm for the for simulating the factorization step, and deterministic of which runtime polynomial of n and log q, and that basically least decodes Reed-Solomon codes up to the Johnson bound. The main the the this algorithm does not give you a general factorization algorithm, because here you have an additional structure that you have a bunch of evaluation points, which in general case you don't have. So because of this additional thing, we basically exploited that additional structure and gave a bivariate factorization algorithm. So I'll just quickly go over the for de-randomization of Gurusamy-Sudan algorithm. I will just give an overall idea. So for this case, let's just assume Q is monic in Y, and we define something called a stable polynomials with respect to the coordinates of the received word. So P, a polynomial, bivariate polynomial x comma y, is stable at jth coordinate if you put x equals to alpha j at that P. Either y minus beta j are the only factor of P of alpha j comma y, otherwise P of alpha j comma beta j is non-zero. So if it is 0 at alpha j comma y beta j, y minus beta j should be the only factor of P of alpha j comma y, otherwise it's non-zero. Notice that the factors we want to look for y minus fx at agreement points or in error points, in both of these places it actually is a stable polynomial. So now so so that's why we in general we just call a polynomial is stable if it's stable at all the locations. And basically we found a connection with stable factors of the q which we interpolated from the first step and the y minus fx. So if p is a factor of q and you have y minus fx to be a factor of p, then you can directly say that whenever f is agreeing with at some point, p of alpha j comma beta j will be 0, and it is an if and only if condition. So if somehow we get our hands on p such that y minus fx divides p, then we can just go over all the points where p of alpha j comma beta j is 0, and from those points we can just interpolate f. So basically we gave a deterministic algorithm that given q, a bivariate polynomial, gives you a list of stable factors of q, and moreover, like whenever you have a polynomial in the list f, y minus f will divide at least one of the stable factors. And naturally the algorithm is basically get all the stable factors, go over all the stable factors and find out where the polynomial is 0 from the received word and just interpolate. And that's how you get that's how basically you list decode. So yeah, thank you.
We have time for questions, or any questions? Let's start with that. Can this algorithm be parallelized, like randomized one?
What?
Can this algorithm be parallelized, like the randomized one?
Parallelized. So the interpolation step, that is a hard thing to do in parallel, like with low depth. And also the factorization step. So recently there is a constant depth factorization using the Furstenberg. So maybe you can use that to do something better. But the main hurdle is the interpolation step, doing the interpolation step in parallel but low depth.
Shouldn't that just solve your system?
What did you say?
We'll talk later.
Okay.
Move back to the front. So does the algorithm generalize to other listicle codes based on polynomials beyond Reed-Solomon?
I mean, you mean to say like the four-digit Solomon University? No, no. The in other cases you have all these other design these subspaces and all. I mean, so in our algorithm we use this Newton iteration and Hensel lifting only specific to the Reed Solomon code cases. Yeah. So in those cases, the interpolated polynomial, it is not two variable, it's three variable, more than two variable. There the problem becomes very hard to do.
Thank you.
Many more questions?
Five.
Okay.
Questions? Buildings for atypos?
So there was a paper on Lebreton and Augur, if I remember it correctly. So they actually de-randomized Sudan's algorithm in the AG code. Okay, anyway. So in the AG code setting, but the Guru Swami, so we are actually trying to improve these techniques to general AG codes. We haven't been able to. But yeah, I mean, the Sudan's algorithm has been de-randomized. So we also gave a Sudan's algorithm de-randomization in a very simpler way using Newton iterations and all. But yeah, Sudan has been done. Guru Swami Sudan we have to see.
Questions? Okay, let's take our speaker